In previous session, we talked about the three states of matter: solid, liquid, and gas. The three states are interchangeable, meaning when you heat a solid, it changes to liquid, and upon further heat, it transforms into a gas. Conversely, if you cool the gas, it condenses into a liquid, and upon further cooling, it turns back into a solid. So, by heating or cooling the different states of matter, we are altering the internal energies of its particles in each state. So, when we heat a solid, it turns into a liquid. But what happens is that the molecules start to vibrate more vigorously. Their kinetic energy increases, and some of the bonds also break. This increases the spacing between them, leading to higher potential energy. The result is a semi organized structure we see in liquids. When the liquid is heated further, the molecules start to move with greater speed and higher kinetic energy. The bonds holding the molecules also break, increasing the spacing between particles. Potential energy increases. Can you fill in the names of processes involved with changes in state of matter? Solid transforms into a liquid through melting, and liquid to gas through evaporation and boiling. Gas cools back into a liquid through condensation, and liquid cools to a solid through freezing. We know that all objects possess internal energy, which is the sum of kinetic and potential energy of its particles. And when we heat a substance, its internal energy increases. This means both kinetic and potential energy increases, but this increase is in a set pattern or stages. In the first stage, the energy is absorbed by the particles to increase their motion and speed. As a result, kinetic energy increases and temperature of the object rises. However, there is no change in the state of matter. If it is a solid, it remains a solid. If it is a liquid, it remains a liquid. As the kinetic energy increases, so does the temperature. In the second stage, the energy absorbed is used by the particles to overcome the bonds holding the structure together. In other words, to increase their potential energy. As the bonds start to weaken, the molecules move further away from each other and change of state occurs. If it is a solid, it melts to become a liquid. And if it is a liquid, it boils or evaporates to become a gas. During this transition or change of state, the temperature of the object remains constant. We discussed previously that in the first stage, energy is absorbed by the particles to increase their motion and speed. As a result, kinetic energy increases and the temperature of the object rises. However, there is no change in the state of matter. If it is a solid, it remains a solid. If it is a liquid, it remains a liquid. As the kinetic energy increases, so does the temperature. We can represent this increase in temperature through time temperature graph. On the x-axis, we have time, and on the y-axis, we have temperature. So an object initially at 1 degrees is heated over 5 seconds, and its temperature rises to 5 degrees. Assuming the object is heated uniformly, we will have a straight line as shown by the dotted line. So if this straight graph was of an ice cube being heated, it only shows that the temperature of ice cube is increasing, but no melting is occurring. We discussed previously that in the second stage, the energy absorbed is used by the particles to overcome the bonds holding the structure together. In other words, to increase their potential energy. As the bonds start to weaken, the molecules move further away from each other and change of state of matter occurs. If it is a solid, it melts to become a liquid, and if it is a liquid, it boils or evaporates to become a gas. During this transition or change of state, the temperature of the object remains constant. So if the temperature remains constant, does this mean that the energy provided simply disappears? Clearly, this goes against the law of conservation of energy. Actually, the energy provided transforms into potential energy and is used to overcome the bonds holding the structure together. As potential energy increases, the temperature of an object remains constant. We can represent this through time temperature graph. On the x-axis, we have time, and on the y-axis, we have temperature. Let's talk about ice, which melts at 0 degrees to transform into water. We leave this ice melting for 5 seconds, keeping in mind that this change of state occurs at constant temperature of 0 degrees. The graph we get is a straight horizontal line. So when there is a change of state, the graph is a straight line parallel to the x-axis. Heating curve is a graph of time against temperature, with time on x-axis and temperature on y-axis. So when a solid is heated until it transforms into a gas, we get the following stepped graph. This graph is a mixture of individual graphs we discussed previously. It is important to recognize the two stages that make up the graph. Stage 1, in which the state of matter is simply heated. As the substance is heated, its temperature also rises, meaning kinetic energy is rising and particles are moving more vigorously. But there is no change of state of matter. The potential energy remains constant. In stage 1, we still have the original state present. So if it was a solid before heating, it's still a solid after heating. If it was a liquid before heating, it's still a liquid after heating, though the temperature of that substance has increased. Stage 2, in which the state of matter is further heated. The substance is heated further, but its temperature remains constant, meaning kinetic energy remains constant. The energy provided is used to overcome the bonds holding the structure together, increasing the potential energy. The particles start to move further away, resulting in a change in state of matter. In stage 2, the substance undergoes change of state. So if it was a liquid before, during stage 2, there will be solid and liquid present. Similarly, if there was liquid before, there would be liquid and gas present during stage 2. The key thing to note is that processes such as melting, boiling, and evaporation only occur in stage 2. This is the stage where heat is used to break the bonds and increase the spacing between particles. Below is a labeled heating curve graph. It not only states the particular state of matter at each stage, but also shows where the change in state of matter is occurring. In this case, a solid is heated until it transforms into a gas. A stepped line graph is used to represent the entire process. First, let's discuss stage 1. In stage 1, the matter is simply heated. The temperature of the substance rises. This is marked by red lines. As no change of state is happening, the potential energy remains constant. Kinetic energy is increasing during this time, but the original state of matter is still intact. We then have stage 2, where transition between states of matter occur. In stage 2, the matter is simply being heated, but the temperature remains constant. This is marked by the brown lines. There is a change in state of matter. The heat energy provided is used to increase the potential energy of the object. In other words, to increase the spacing and break the bonds between particles. Melting and boiling all happen during this stage. In your syllabus, we need to know certain definitions. Melting point, the definite temperature at which a solid changes into a liquid at constant temperature. Boiling point, the definite temperature at which liquid changes into a gas at constant temperature. Evaporation, the process in which liquid changes into a gas at any temperature below boiling point. I am confident you have encountered these terms in your earlier studies as well.